Hey guys, welcome to Digital Srini channel on YouTube, and I hope you have subscribed to this channel. If not, this would be the right time to do so. For the last for the last dozens of videos, we have been focused on semantic segmentation using UNet. And we have used our own UNet where we defined a simple UNet with every little convolution 2D, every operation where we define that in a separate line, right, using our Keras sequential method. Now, in this video, let's understand the UNet architecture again. And why now? Because we have done enough UNet to have a good knowledge of what this is. So it gives us, would be the right time to get back and look at, do I understand it in the right way, first of all? And then how can we build this UNet model from scratch in Python? Well, we have done that, but let's look at some patterns. Are there some repeating patterns? Meaning, can we define these as functions? And then define our UNet in a very simple way. So in future, if you would like to write your own UNet by expanding the number of convolution blocks, you can do that, right? So of course, go ahead and use others' code, use other libraries that make your life easy. But this can be very useful, understanding this. So let's go ahead and jump in to a few slides, and then I'll also, after going through these slides, we'll go through some code, and I'll share the code. So please pay attention to this tutorial and take notes, but don't try to pay too much attention to every line, every detail yet. Okay, maybe when you watch this the 5th time, you can do that. Okay. First of all, this is the UNet from the original paper, and they have used image size 572 by 572 and one channel, and then 64, 128, and so on. So this can be a bit difficult to follow because of these dimensions. So I kind of changed that into something that takes in an input of 256 by 256 by 1, right? So typically we work with images that are 128 by 128 or 256 by 256 and so on. So let's focus on 256. Again, it doesn't matter what the input size is, but this makes it easy intuitively for us to understand what's going on. So here is what we have written as part of our simple UNet. What did we do? We added convolution. First of all, we have an input layer of 256 and 256 by 1, right? And then we have 2 convolution layers. So look at that. You have this input, and then you have 2 convolution layers. What happens then? You have this red arrow, which means max pooling, okay? And after max pooling, you again have 2 convolutions. So let's go to the next one. Okay, so convolution, max pooling. Con, max pooling, con, max pooling. How many of these? We have 4 of these, right? So if you go back 1, 2, 3, 4, and then the 5th one is our base, and then it goes up from that point. Okay, so the 5th one is our base right there, and then it goes up, which is our decoder path. Okay, so again, we'll get to these in a minute, but I took this code, right? I mean, we look at this and you see what size, here you have 64 filters, 128, 256, 512, and 1024. Exactly the same, 64, 128, 256, 512, and 1024. So I kind of redid that original image to reflect these new dimensions. So 256 by 256, right? Our input image, 1 channel. It doesn't matter. You can have 3 channels if you want. And 64, in fact, you can have multi-channel, right? Not just 3 channels. If you're dealing with remote sensing or some sort of multispectral data, you may have 256 by 256 by, 10. Okay, but let's just focus on 1 first. So 256 by 256, and then after the first convolution, the first convolution operation involves 64 filters, and the next one involves 64 filters. Okay, so these are 64 images that it's actually generating for every image that you have here, right? So that's what that means. And then you have your max pool operation of 2 by 2. What does max pool 2 by 2 do? We have to understand every step here. So when you do this convolution, the convolution is a 3 by 3 kernel. And after the convolution, we are applying a ReLU activation function. Okay, so that part I hope is clear. And then comes max pool of 2 by 2. When you apply max pool of 2 by 2, you're applying a 2 by 2 kernel onto your image. So your output is going to be half the size. That's why I started off with 256, so it's intuitive for us. Half of 256, 128. That's why you see 128 by 128 here. Now, why does it show 128 right there? because when we define our convolution layer right here, we define that we want 128 filters. Okay, so that's exactly why we see 128 right there. Okay, this is our number of filters equal to our number of features equals to 128. Okay, again, 2 convolution operations, then comes another max pool. What happens with max pool? This dimension 128 is halved. So we have 64 by 64. Now, why do I have 256 here? Again, that's exactly what we defined there. We want 256 and we have 256. This continues all the way up to this point. Okay, so here we have 16 by 16 and 1024 is the number of features. Again, that's because that's exactly what we said we want. Okay, now this is my base. This is my base, and going up, what's happening while we are going up? Okay, so pay close attention here. So from 1024 it's going to 512. Why is it going to 512? Because that's what we defined, right? So going up, there is a convolution operation, okay, of 512. Okay, there is a convolution operation of 512, and the green is up convolution 2 by 2. What does that mean? It's upsampling. So it's going from a size of 32, okay, to a size of, where's my image? Sorry, wrong image. It's going from 16 size to 32 by 32. And from 32, when you do upsampling, yeah, it goes to 64. Again, you can use convolution transpose operation, or you can use upsampling. Please watch my previous video, exactly the one before this, for a good explanation of what is the difference between these two. But either way, you're upsampling it from a smaller dimension to an upper dimension. If you're just upsampling, it just copies your rows and columns and doubles it. That's it. Okay, so that's exactly what the green arrows indicate. Now let's understand this concatenation part, because this is very, very important, and this is what makes the semantic segmentation possible. Because here, you normally, if you don't have this concatenation, or these are typically called skip connections. If you don't have this, then this is not a unit. This is just a one fully connected, sorry, not fully connected, one convolutional neural network. That's it, right? I mean, if you don't have this concatenations. So here we are going from 1024 to 512. Again, that's because we are going from 1024 to number of convolutions 512. Okay, and then as soon as you do that, okay, we are concatenating S4 and D1. What does that mean? After we do this, I mean, do this operation, upsampling, we are concatenating these two, meaning these filters, we are adding the filters that we got from the previous step as part of your encoder path, combining them together. So we have double the number of features at this step. Normal forward, normal convolution neural network, you only have half of these, right? So now we are concatenating this and following this convolution steps again, right? I mean, what happens after we concatenate these two? Convolution of 512. And then what happens? Another upsampling step, right? So now let's go back and look at that. So after this is done, my 32 by 32, I do my upsampling. What happens when you do your upsampling? Well, your 32 becomes 64. Okay, you still, and then why do you have 256 here? Because that's what we defined. We want number of filters to be 256. So you have 256 right there. And to that 256, we are tagging another 256 that comes from this layer that has 64 by 64 size. The same dimensions, right? They have to be same dimensions. Otherwise, you cannot concatenate. So we are taking this and we are adding it to this. So on the whole, you're actually getting 512 right here. This exactly provides the context at different scales, at different parts of your unit. Again, read the original paper if you really want to understand this even to that level. But this concatenation makes it possible for it to get the context, okay, from a different level right here as part of your neural network architecture. So we are just concatenating, and if you look at this, this is just a symmetric way of concatenations of these features with the next level features. That's it. Okay, so I hope things make a bit more sense right now. I'm hoping you paid close attention before. If not, this definitely helps. Now let's take this to the next level. Okay, what does that mean? Let's say, what output do we get out of here, right? I mean, think about it. You have an input image 256 by 1. you apply 64 filters. I mean, you extract 64 filters out of this, and then another 64 filters. I mean, in the next convolution layer. So the output of this is, let's call this S1. This is just an output of the convolution layer. Okay, these are the number of filters, number of features. Now, when you do this max pooling, the size of the image is going from 256 to 128. Let's say that output is P1. Okay, now let's think about it. What gets concatenated is S1 from this layer to that layer. Okay, what gets passed on to the next layer, next level, is P1, because after max pool comes this block, and same thing repeats. You have a convolution, and then the output of this convolution operation, the output of the convolution block, let's call this block convolution block. The output of convolution block is the one that gets concatenated with this other convolution block as part of the decoder. But the output of the max pooling is what goes to the next level. Okay, so how do we define this? So now let's again say the output that we are getting here is S1 and P1 from this entire block, including the red arrow. Here it's S2, P2, S3, P3, and so on. So let's just give some names to this, so it makes it easy for us to program it. Okay, that's why I'm giving these names. So S1, P1, again, S1 is the output of the convolution block, and P1 is the output of the max pool of the first convolution block. Let's call this an encoder block, okay, this entire thing. So that's my P1. The whole job of P1 is to be the input to the next level. The whole job of S1 is to be the array that gets concatenated with the symmetrically equivalent layer on the decoder part. I hope so far you're following. Now, let's look at these blocks that are repeating. Okay, let's only look at this top block. These are the, let's call them the convolution blocks. Again, what is the purpose of this? We can concatenate the output of this with the input that's going into this layer, right? So this is a block that we need to define as a separate function, because now you just run that function and whatever the output is, it goes to the input right there. So it's pretty easy. What do we have in this function? Well, first of all, what goes into this function is the input, right? Whether it's here or there, it doesn't matter. There is an input that goes into this convolution block. And then we also need to define the number of filters. Here the number of filters are 64, here 128, here 256, right? I mean, and so on. So these are the two that go into this convolution block function. And then what happens? Then conv2d operation happens. In this example, I included batch normalization. I don't think in the original paper there is batch normalization, so you can add batch normalization, you can add dropout if you want to add a regularization term, and so on. But the key here is this block, the blue arrow, represents a convolution operation with 3x3 size and followed by ReLU activation. That's it. That's what the blue arrow is. And that's exactly what I'm defining here. Conv2d with how many ever number of filters, in this case 64. With a 3x3, you can define this as 3x3, but just 3 implies that this is 3x3. And followed by ReLU activation. How many of these do we have? 2, right? Another conv2d, batch normalization, and activation. That's it. This entire thing is this blue box. And that blue box repeats. If you look at that, it repeats even while it's going up. So it does make sense for us to define this as a separate function. Now let's also define an encoder block in a separate function. Encoder block is nothing but our convolution block with max pooling added to it. That's it. Why do we need to define encoder block as a separate block? That's because that output of that encoder block goes into as the input of the next encoder block. That's the reason. And the reason is, again, we want both S and P. The previous one only gives us S. This operation gives us S and P, both together. So how do we define it? Well, we already defined our conv block in the previous slide, right? So this is our conv block. So all we need to do is call that conv block and perform a max pooling operation. So we get two outputs from this encoder block. One is X and the other one is P. I should have called this S to keep the terminology the same, right? That's what we have been using, but this X is nothing but our S that we just defined, and the P. That's it. Now, so we are done until this point. Now, how do we tackle the this part? Now let's define a decoder block. Now, are these repeatable? Yes, of course. If you look at the first step that happens in the decoder block, this is the green arrow, which is up convolution. So once you get the output of the encoder block, what do you need to do? First of all, up convolve or transpose, right? Conv 2D transpose, which takes the image from 16 in this example to 32, right? It doubles. And then you tag along, you copy this right there, okay? You copy or concatenate these two and then perform two convolution operations. Okay, let's look at the code and hopefully that makes sense. So first of all, what are the inputs to this decoder block? One is the input, from here, the input array coming from the previous operation. And then you need the skip features. What do we call by skip feature? What do we mean by skip features? Skip features is nothing but this block right there, output from there, output from that conv operation that gets concatenated. What is that? We'll see why we need that in a minute. And we also need number of filters, right? 512 or 256 or 128 or 64 as we go up. So once it gets these inputs, what does it do? Well, first operation is transpose, conv 2D transpose or upsampling. I'm using conv 2D transpose in this example. Okay, so that's the green arrow right there. So it requires the number of filters because this is a convolution operation, and it's a 2 by 2 operation, and the number of strides equals to 2, which means it's doubling the size from 16 to 32. And padding equals to same means pad it such a way that my output is same as the input shape. That's pretty much it. Okay, so padding is same, and once you have the transpose or upsampling, the next step comes concatenation. So we are going to concatenate two things. What are X and skip features? X is the transposed output, right? This one, and the one coming from before. So let's repeat that for, let's say, this block. Okay, here it's too busy. Let's repeat the decoder blocks up here. So first, input. Where is it coming? It's the output of this previous one, right? So that's clear. So first operation is on the input, we are going to perform conv 2D transpose using how many filters? In this case, 128 filters. Okay, so using 128 filters and 2 by 2 and a stride of 2. So that means sorry for confusing you. Sorry for confusing myself. The input is coming from here. So my number of filters is 128, correct? But my image dimensions are going from 64 to 128, right? So this is stride equals to 2. So it's going from 64 to 128. To that, we want to concatenate what? We want to concatenate X, meaning this, with whatever that skip feature says. We have to define what that skip feature is in a minute. So that skip feature is coming from here. Okay. Hopefully next slide will make things a bit more easy if this is not easy enough. Okay, and finally, after this, we are going to add a convolution block, because remember, this part is nothing but a convolution block. It's two convolutions with ReLU activation. That's it. That's my convolution block. So this is a conv block. And what does convolution block require? It requires the number of filters as input, right? It's 128 here, and our X, which is the input coming from this concatenation. I hope this again makes sense. If not, let's do one more thing. Okay, so this is the same slide that we saw earlier, where now we actually put some names here. Let's say this is S1 P1, S2 P2, and so on. Now let's put together our final unit code. Now that we have all the functions, this is your final unit code. That's it. Okay, very few lines. Your input is whatever the input shape is here, 256, 256, 1. And what happens next? Let's define this. S1 P1. This is the output of the operation that happens here. What is that? That's nothing but our encoder block, right? So this entire thing is our encoder block. I hope you guys are with me here. So this is our encoder block. Everything including the red arrow. Okay, the output of this is S1P1. That's exactly what we are looking at here. S1P1 is the output of encoder block, and it requires input and number of filters. What is the input in this case? Because this is the first one, the input is my inputs, right here, and 64 filters. The next one, S2P2. What is this these outputs? Again, encoder block gives us two outputs. Remember, one is just the convolution block result, and the other one is the max pooling result, which is P. So S2P2 is basically our encoder block with an input of P1, because remember, again, the whole point of your max pooling output is it goes as input to the next block. Okay, so P1 and how many filters? 128. So repeat this 4 times until you get down to 512 right here. And then the base block is also a convolution block. It's not a full encoder block if you look at this base block here, because there is no max pooling after these operations. That's why I separated base block down here with a convolution block. So there is only 2 convolution operations, and my number of filters is 1024. Obviously, the input is going to be P4 because that's coming from here. So if you put this thing on a paper, you can design your own unit and just write it in with a few lines of code. Okay, now comes the decoder, and we know what the decoder block includes. It includes the green arrow, the concatenation, and then these 2 blue arrows, which is nothing but our convolution block, right? So we already defined that as part of our decoder block. So our decoder block requires 3 inputs, if you remember. Let's go back. So as you can see here, it takes 3 inputs, right? So one is the input from the previous block right here. And then the next one is skip features. These are the features that are coming from the symmetrically opposite encoder block, and the number of filters. So if we go back here, now you can actually see that our decoder block, the first one, let's focus on this D1. Okay, so what's D1? How do we get the output D1? Well, by applying a decoder block right there, that function. So what's happening there? First of all, it's taking input from B1, right? So after this, we are getting an input of B1, and once it's done, once this up convolution is done, because again, as part of our decoder block, we have the transpose or upsampling, and then comes the concatenation, right? So this is what we're trying to get to. So the next step is concatenation. What do you concatenate that with? With S4 in this case, right? So here you have this block, I mean these features that are coming from here, and then these features that are copied from here, S4. I put S4 down here, don't be confused. S4 is the output of this one, right? And the output of this red arrow is P4. So this S4 is going to be joined with this to give us D1. Let's focus on this block for now, okay? The next one. So what happens? D2. Okay, so our D2 is our decoder block function with inputs of D1, because D1 is coming from the previous block. And then what are we concatenating this with? Our S3. Remember, this output right there is S3. Okay, the S3 is concatenated with this, and then how many of these features? 256. So you can work your way back all the way up to here, and in fact, up to this point is your D4, and what happens in the final output layer? Your final output layer is a convolution operation with 1 output, because this is, in this case, we just want a output image that just has like 1 channel. That's it. Okay, with the corresponding classes. So we have a sigmoid operation right here. So I hope this clarifies any questions that you have, and I hope I haven't confused you. But let's go to our IDE to define this exactly, and then see how our training actually goes. And let's actually write this code, right? I have written that. Let's do this from scratch and see if the results actually make any sense. Let's do everything live, so I'm not showing you some theoretical stuff that may or may not work. Okay, so before jumping again, let's summarize this one more time. It does make sense. I know that it makes the video a bit long, but I really want you guys to understand the unit architecture. So It's basically, we have defined these into individual blocks of convolution block, encoder block, and decoder blocks. A convolution block is just these two convolution operations. Because that gets repeated, we just separated that as a convolution block function. Encoder block is nothing but convolution block where max pooling is applied to the output. That's it. And why do we need these two? Because the output of convolution block is used as our skip connection or concatenation right here. And the output of max pool is the input to the next layer. So we did that until we get to the base. And at the base, we realized this is not a encoder block because there is no max pooling. It's only convolution block. And from here, we switch to decoder block, which starts off by up convolution or transpose, con 2D transpose operation, where it doubles the size of your image along this dimension. So 16 by 16 to 32 by 32 to 64 by 64 and 128 and 256. Okay, so that's what that up does. And then the next immediate step is concatenation with the skip connection part right here. And then on the combined data, we are applying two convolution operations. And then we keep doing that all the way up to this point, at which point we slap in this output layer, and then we get the output here. Okay, so now let's switch to our IDE. Again, it doesn't matter. I'm using Spider. You can do this in Google Colab or anywhere you're comfortable with. Okay, so let's switch to our code. Okay, so here's my IDE, and I'm going to work with the same data set that I have worked with a couple of tutorials ago, where we only have 12 images, about 150 labeled objects, in this case mitochondria. And where can you get this data? Well, I'll provide the link down below, but you can just search for mitochondria, data set, EPFL, or just look at the link down in the description. Okay, and this is a full data set that contains 165 plus 165 images, so you have enough data for good training. But I only took 12 images out of that. So if I have those, yeah, I do have them. So I only took 12 images right here. That's it. And why did I do that? Just to see how good of a segmentation we can actually do with transfer learning. And please watch that video a couple of videos ago. Okay, now we're not going to do transfer learning. We are only going to do just whatever unit we are going to write right now, and use that and see how good of results we actually get. Okay, so let's get back here. And first of all, let's start by looking at the unit model. This is exactly the same as what you have seen in my presentation. So this is the convolution block that I have defined. Again, convolution block takes input and number of filters and returns us an output, right? That output goes into the concatenation layer. Now we defined encoder block, and encoder block is nothing but our conv block, followed by a max pooling operation of 2 by 2. And this gives us two outputs, which is our encoder output and also the output of max pooling. And X goes, again, I mentioned this a million times, as part of concatenation, and P would be as part of your input to the next layer. Now, finally, the decoder block it takes three inputs. One is your input from the previous layer, and the next one would be the skip features. And these are the features that's nothing but your X, but X from a relevant layer, not from any layer, right? And number of filters. So this is, and it includes the conv 2D transpose and concatenation of these two, and then the convolution block, and you get an output there. Now, here is the build unit, and this is where we ended our presentation by looking at, okay, so my S1 and P1 is nothing but our encoder block output, where it takes in inputs and 64 number of features and so on. Okay, so we already talked about this. So this is the model that we're going to use. And as part of the data set, I explained this data set so many times. So let's go ahead and only run these lines of code. This is nothing but our libraries that we are importing. And then these are the two images I literally showed you. And this is a TIFF stack, meaning a single TIFF file that has 12 images, a TIFF stack. So to better read these, I'm going to use TIFF file library, TIFFFILE. So let's go ahead and read that. Again, all of this we have done many times. So each image is 768 by 1024. We have 12 total images. And then comes extracting patches from these images, and for that I'm going to use Patchify. I explained this many times, and Patchify extracts individual patches from these large images, and I am extracting 256 by 256 patches because that's what my network is expecting as input. And I'll do exactly the same for all the masks. Go ahead and divide the masks into all of these 12 images and each image into 12, so total 144 images and masks. Next comes dividing my my data into training and testing. Of course, you know what that is. Let's expand this a bit so you see what's going on the right hand side. And now I always do this sanity check no matter how many times I run this. And the sanity check is I'm just plotting my images against the masks just to make sure, is everything divided in the right way? Yep, there you go. You can see that that looks good. That looks good. You see the mitochondria there, so we are all set. Okay, now let's go ahead and define our model. So our model takes, it needs the input shape, right? So our input shape is basically our images.shape, which is, let's go ahead and define our input shape. And input shape is 256 by 256 by 1. Yeah. So next comes our model. So we need to build our model. So how do we do that? Well, we are importing from unit models with functions of blocks. I'm importing build unit. That's basically this part, right? Build unit. Okay. And it's going to build this unit. So let's come back here, and where are we? Go ahead and build unit right there. Okay. And once you have that, of course, as part of this unit, we haven't compiled anything. We need to compile this with by providing a optimizer. In this case, I'm using Atom optimizer, binary cross entropy as loss function, and matrix accuracy. That should be fine, I believe, right? Yeah. And finally, let's go ahead and print out model.summary. And there you go. This is the summary. You can spend a lot of time trying to understand this summary. Okay. So 256 by 1, and then 64 filters, and then comes your activation, and then these. So this is our single convolution block, and then comes your max pooling. Okay. And then comes another single convolution block. So go ahead and study this. Okay. Now let's come back, and we are ready to train, but just with 12 images or 144 of these tiny patches like 256, we're not going to get good results. So let's go ahead and use data augmentations for both images and masks, right? And I'm fixing the seed to 24 or whatever number, it doesn't matter. I'm fixing the seed, so any transformation that's happening with your images are exactly repeated for your masks. You want images and masks to be exactly the same, okay? So let's go ahead and run all of these lines up to here, which is basically defining the generator. Still, let's continue our generator part. Again, I explained this in detail in past videos, so let's not waste anyone's time by defining, redoing this. But one final thing before moving on, let's go ahead and check our generator. Yes, now these are the images that our generator is generating. This is my input image, and that's the mask. Okay, so let's go ahead and check a couple of these. Yep, it seems to be doing an amazing job right there. All of these are augmented. Yeah, meaning none of these are actual original patches, but they're transformed one way or the other. Okay, so I think we're good. Let's define steps per epoch. I'm leaving this to this steps per epoch, which I think is 40. Let's look at steps per epoch. 40, because this worked out for us the last time. And now let's fit the model. Let's go ahead and let's only do 25 epochs. Again, if you test this out, go ahead and do 50 epochs. Even this probably takes some time. I have GPU, I have 16 GB GPU, so I have very good GPU, but I hope, well, it's take 15 seconds. So to do about 25, so let's come back in about 10 minutes to look at the result. Okay, so let me go ahead and pause this video. Okay, so finally this is done. So let's go ahead and have a quick look at the results. And after 25 epochs, I got an accuracy of about 98% and IOU score of 71%. 71% IOU is not bad with this type of data. First of all, let's go ahead and see how our plots look like. Okay, let's go ahead and look at these plots, and they're probably here. This is what I expected. You see how our validation loss is jumping up and down, but eventually it came down. It's jumping up and down because we don't have good enough validation data, right? I mean, we don't have a lot of data. We have a handful, and we are doing that. We are transforming it, but it's still not a lot of data. But this is good trend. And looking at accuracy, again, it jumped up and down, but eventually it settled down. So I'm a bit hopeful about the results right here, even though we put together this from scratch, right? So this is not a fancy transfer learning or nothing. So IOU, we already looked at the values, but if you want, let's go ahead and print it out one more time. So IOU is 71%. So that's also pretty good. Okay, now let's load some random images, predict, and plot both the ground truth and the prediction. So this is the moment of truth. So let's do that, and let's expand this a bit so the images look a bit nice. So there you go. So that's the ground truth label, and this is what we got. That's not bad, but that's not a great image. So let's do this. So yeah, this one, these two mitochondria, here is the ground truth, and here is our prediction. Again, I'm super impressed by this. And let's look at the other one. So again, this is the ground truth, and this is what our prediction is. In fact, I like my prediction better than ground truth because I start to see a mitochondria right there. You see that my prediction is actually giving that mitochondria, but the ground truth, for whatever reason, didn't have that. Same thing up here. Here you can see how this is not, I mean, we are seeing some issues right there, right? So we don't have a good definition of our mitochondria there. Here it wants to show something. But overall, I'm pretty happy with the result. I mean, this one has nothing. There you go. I mean, we already saw that. Another one. This one is almost identical between these two. I mean, again, we may be a bit exaggerating this mitochondria right there. Maybe a few more epochs would give me much better results. But I hope the point, I mean, you get the point here. We literally defined everything from scratch here. I zoomed out so you can see, but we defined a convolution block, we defined an encoder block, we defined a decoder block, and then we built a unit by just saying, okay, I want 4 encoder blocks and 4 decoder blocks. Now you know, if you want 6 or 7 encoder blocks, go ahead and do that. See if the deeper network really helps you. But when you're doing that, make sure as part of encoder, I mean, in this case, we include batch normalization, but try to include dropout so you're not overfitting it, in general. Okay, so this is already a long video. I don't want to extend this any further, but I really hope you enjoyed this. I'm pretty sure you did. Otherwise, you won't be watching this till its end. Again, please go ahead and subscribe to this channel. Thank you, guys.